Momentum is what we're going to call a conserved quantity, which kind of means that as long as there's no external forces, it's never going to appear or disappear. So momentum, and we'll talk about energy in the next lecture, is going to be what we call conserved, never going to go away. Now, what the law of conservation of momentum says is, as long as there are no external forces in a system, then the momentum of the system is going to remain unchanged. So think about this in the language of a cannonball that's being fired. Now, initially, these guys have some momentum, and that momentum is actually going to be zero. The cannonball is at rest, and the cannon is at rest, and then the cannonball is going to go flying off in this direction after the cannon goes bam, and the cannon is going to recoil. And what that means is maybe the cannonball has some positive momentum. This guy, the cannon, is going to have some negative momentum. It's going in the negative direction, and these two need to add together such that they equal the momentum of the system beforehand, which is going to actually be zero. And you'll be able to see this numerically in a couple of slides. Now, what's kind of going on here is Newton's third law is when the cannon is fired, the force on the cannonball is going to be equal to the force on the cannon in the opposite direction, so positive direction and negative direction, if you will. So the cannonball is going to gain momentum in the positive direction. The cannon is going to get the same amount of momentum in the opposite direction, the negative direction, and as I said earlier, they're going to add up to be zero, which was the momentum of the system beforehand. Now, a key word to look for is external force, and you might be saying, okay, well, there was gunpowder, it went bam. That was internal to the system. So as long as no one comes up to the cannon and pushes it, then momentum will be conserved. The gunpowder was internal to the system. So let's just talk a little bit about some internal forces. If we consider just a baseball, yes, there are tons of molecules inside of them held together by chemical bonds. These are all internal to the system, and they're not going to have any effect on the momentum of the baseball. Just like if we were to push against the car's dashboard, we really can't change the momentum of the car. We can only change the momentum of the car if we were to physically push the car, which is going to be an external force. So pretty much for this class, for all collisions and explosions, then we're going to say momentum is going to be a conserved quantity. I'm never going to give you an external force. So when we say the net momentum before has got to equal to the net momentum afterwards, we can kind of write this in equation form, where this is the momentum before and this is the momentum afterwards. And one word to pay attention to is that word net. And that's kind of a special word for a sum of. So if we have more than one object, we have to add together all of the momentums. And you'll see that in the next couple of slides. Now let's take a quick look at this before we do some heavy math on the next page. If you consider myself and this ball, we're a system, and our momentum before is zero. My speed was zero, the ball speed was zero. Anything I did cannot change that momentum. The momentum's got to be zero. Even if I sit down and throw the ball, the ball's going to have a positive momentum, mine's going to be negative, and it still won't be equal to zero. Now, kind of as you saw in the demo, that was kind of an example of an explosion, and that was going to be a case where momentum was conserved. So what we're going to do is we're going to say net momentum before is equal to net momentum afterwards, and so that's going to be the mass times the speed of the professor plus the mass times the speed of the podium. I'll call that a S for stand. So mass of the stand, velocity of the stand. And what I kind of did is that this word net means I add them together, and afterwards there's going to be some new mass of the professor, speed of the professor, and that little prime there just kind of means afterwards. And then there's going to be mass of the stand, speed of the stand, and that little prime is going to mean after the explosion occurred. And we do know initially that I had a speed of 0 and the stand had a speed also of 0, so the net momentum beforehand was 0 kilograms meter per second. Now afterwards, well, we're going to have two speeds to worry about, and one thing to kind of keep in mind is I'm going to say that maybe I was going off in the positive direction and the stand was going off, that's going to be the professor, that's going to be the stand in this direction, and we're calling that direction negative. So what we can kind of say is the mass of the professor, speed of the professor afterwards is going to be mass of the stand, speed of the stand afterwards, and actually I'm kind of moving one to the other side, so that's going to be a negative sign. And you can kind of see that these two guys are going to essentially be equal to each other. Here's another example of the conservation of momentum, and don't try this at home. Here we have a system of some gas and a rocket, and initially their speeds are equal to 0, so the momentum is equal to 0. I'm going to go ahead and ignite this guy, and the gas is going to come flying out of the back at a very high rate of speed, and the cart goes in the opposite direction. Now when we talk about collisions, there's two types of collisions we can talk about. We can talk about elastic collisions, and elastic collisions, there's going to be a conservation of this thing called energy, and we're also going to say that momentum is also going to be conserved. So both energy and momentum are going to be conserved. And what happens in elastic collisions is there's going to be a perfect rebound without any deformation, noise, heat, or anything like that. So, at the end of the day, if these two carts were to collide, then if they had the same mass, then this guy is going to have a speed of 0, and the green one is going to have a speed that's equal to 10 meters per second. Why? Because this one initially had a speed of 10 meters per second. And again, what we could kind of say is we can kind of say that the momentum beforehand has got to be equal to the momentum afterwards, and that's going to be the net momentum. So it's going to be momentum of this guy plus this guy, and the momentum afterwards is going to be the momentum of this guy plus this guy. And I'll work this guy in 2 slides after I talk about the next type of collisions, which is going to be inelastic collisions. And inelastic collisions occurs when objects collide and there is deformation and there is generation of heat, there's sound, there's noise, and all sorts of things. And at the end result, what's going to happen is they're going to stick together. So if you ever see the word stick together, then that means that you're talking about an inelastic collision. Now, don't have to worry, in inelastic collisions, momentum is going to be conserved as well. However, energy is not. Some of that energy is going to go into the banging, the heating up, and stuff like that. And what this guy would kind of look like is these guys are going to go bang, and then they're going to stick together. So there's my red guy and there's my green guy, and they're going to share the same speed, some new speed after the collision, and it's definitely going to be less than 10, and that less than 10 just kind of means energy was lost. So let's just do a couple calculations. So here, coming back to my elastic collision where we had car A was moving at 10 meters per second, it looks an awful lot like that one 2 slides ago, and car B had the same mass and it was initially at rest, and that's kind of a key word for saying that the speed of car B initially was equal to 0. And then after the collision, car A is at rest, just kind of the way that I drew it, so that's kind of saying that the new speed of car A is equal to 0. So conservation of momentum is going to say net momentum before is equal to the net momentum afterwards, so mass of car A times the speed of car A plus the mass of car B times the speed of car B is going to be equal to the mass of car A, the speed of car A afterwards, plus the mass of car A, the speed of car B afterwards. And kind of what we're looking for is we're looking for the speed of car B, and initially we knew that car B had a speed of 0, car A had a speed of 0 afterwards, and actually these guys shared the same mass, so we're just going to say the mass of car A times the speed of car A, which was equal to 10, is simply going to be equal to the mass of car B, which is just m, times this new speed of car B. And you can kind of see that these masses are going to cancel out, and lo and behold, just like I told you 2 slides ago, the speed of car B is going to be equal to 10 meters per second. Now let's take a look at that inelastic collision. So here we're going to have a single car of mass m, it's moving at 10 meters per second, just like it was on the slide, runs into another car that was initially at rest, so calling this car A and this car B, this tells us that the initial speed of car B was equal to 0, and they stick together. Very, very, very important word. Now what that kind of means is, let's write the net momentum before and the net momentum afterwards. So the mass of car A times the speed of car A plus the mass of car B times the speed of car B. Now they stick together, so we're actually going to add their masses. So mass of A plus the mass of B. And now they're going to go off and they're going to share some new speed, kind of that V prime. Because it's the same, I really don't have to denote it A or B. Now, we know that this guy was initially at rest, so what we're left with is the mass of car A multiplied by 10, and this is going to boil down to 2m, because mass of car A and mass of car B are the same, so we just add those together and we get 2m times this new speed. And again, the masses are going to cancel out, and this new speed is actually going to be a speed of 5 meters per second. So you might want to try to work this one on your own before you watch my solution to it. Here we're going to have kind of the same setup. We're going to have a car of mass m, and we're going to call this car A. It's moving at 10 meters per second, and it's going to collide with another car of similar mass. So we're going to call this one B, and it's moving 5 meters per second towards the first car, and they're going to stick together, so inelastic collision. So I kind of drew this guy right over here, and one thing to keep in mind is his direction. Positives and negatives really matter, and let's just for the sake of argument call this side positive and this side negative. So car number A is going to have a positive speed, car number B is going to have a negative speed. So we're going to do the same thing. We're going to have the mass of car A times its speed, which is going to be a positive 10, plus the mass of car B times its speed, which is now going to be very careful here. That's a negative 5. Negative just means that it's going in this direction. And that's going to be equal to, we're going to add the two masses together, so 2 times the mass times their new speed. And what we're kind of left with is right over here, these guys are going to, well, subtract, and we're left with 5 times m. That's going to be equal to 2m times the new speed. And much like last time, all the masses are going to go away, and the new speed is going to be equal to 5 divided by 2, which is 2.5 meters per second. Now, sometimes people don't like it when I just have to cancel out the mass like that, so this is just an example where I've got the same setup. I've got car A and I've got car B, and I do encourage you to try to do this guy on your own before you watch my solution. Something to keep in mind is that the speed of car B is going to be equal to 0 initially. So we're going to have mass of car A times its speed plus the mass of car B times its speed, so A and B. It's going to be equal to, well, it looks like they stick together again. So it's going to be the mass of car A plus the mass of car B times their new speed. And what we can kind of do is we can kind of say, okay, well, this is going to be 5, that's the mass of car A, times its speed, which is going to be 2. And then this guy is going to be equal to 0. So I'm going to go ahead and add these two guys together. 5 plus 10 is going to give me 15 times the new speed. And so what we're kind of left with is 10 is equal to 15 times the new speed, which after you punch that into your calculator, the new speed is going to be 0.6 repeating meters per second. Now, we can have more complicated collisions, and in that case we're just kind of looking at collisions in 2 dimensions, and essentially what happens is momentum still going to be conserved, and it's just going to be kind of conserved in both directions. Now, the math to this gets really hairy, so I don't expect you to be able to do the math, but I would like for you to kind of know that if you have a car going this way and a car going this way, then the car A's momentum is going to be in kind of this direction. Right? Call this car A, call this car B, so momentum of car B is in this direction. And kind of if you add those two guys together, it's just like the forces, where if you have a force in that direction and a force in this direction, then the net force is going to end up in this direction. You would kind of expect that if these two cars were to collide, that the wreckage would kind of go off in that direction.